5, we have to understand the power system reliability and security. So you know that the power system authority always should ensure reliability. So they have to be designed to provide electrical supply to the consumers economically, continuously, and of good quality. Power quality should be good without any distortion. And also they have to dispatch the electrical power economically, and it is continuously, it should be continuous. Modern power systems are very complex. You know that if you see from the generation to the distribution side, we have, after the generation, we have primary transmission network, then secondary transmission, then primary distribution, secondary distribution. We have a large network. It is very complicated, complex network, and they are highly integrated. Even the blackout for a small duration, it causes massive losses to the economy. So to reduce the probability of occurrence of such events, it is very important we have to reduce the frequency and duration of grid failures. So for this, during planning and design, we have to invest. So we have to carefully design the system. So this is to ensure the reliability. Now, it is mainly classified into two aspects. System adequacy. So it refers to the existence of sufficient generation, transmission and distribution facilities to meet the consumer demand at all points of time. Adequacy requirements have to be considered mainly in the planning and design phases. So during the planning and design also has to be planned. So we have system security, another classification based on the system security. It refers to the ability of the system to meet demand under dynamic disturbances in the system. Generator outage, line outage, generator outage as well as line outage. So it is even under this condition, the system has to be stable under the loss of largest generator. So we have to ensure security also. Then central point of network security, it is associated with the probability of maintaining adequate supply in the event of contingencies. See, contingency, you know that is during the failure of any equipment. Maybe any one equipment is out of service. It is not available for service. It is under failure. So even under that condition also, the system should maintain adequate supply of power. Okay. So then we have contingency that refers to the loss of generator unit or transmission equipment. So contingency analysis involves an analysis of all possible contingencies likely to occur, detect the critical ones, cause violations in the voltage, line flows. It may be even active power, reactive power, and even current, and rank them according to the severity. See, when you are doing the contingency analysis, so as I told you earlier, so this will be done using simulation package, because in a large power system, we have to simulate the loss of any one generator. If any one generator is out of service, what will be the power flow in the line? What will be the voltage at various buses? What is the power flow in the line? All these have to be analyzed. So for this, we use the simulation package, like you have used my power for load flow in earlier semester. So here also we will use some simulation package to do the contingency analysis. So when you simulate the outage of transmission line or outage of generator, so all these parameters will be estimated. There will be deviations in the voltage, line flow, power, active power, reactive power, and once you do the analysis, we have to rank them, which is more severe, which outage, whether transmission line outage or generator outage. Maybe in a system you have so many generators, which generator outage will be more severe. So all these things can be analyzed. We have security levels of system. To develop a security system, the power system security levels are classified based on the severity. Level 1, level 2, level 3, level 4, level 5, level 6. See, this is similar to you have studied in module 1 about different states of the system. It is similar to that. So recall that. So we have level 1, that is, it is considered as secure level, where the load is supplied without violating any limits. See, that means the generation and the load demand is balanced. load is supplied without violating any limits. See, when you consider the parameters like voltage and frequency, mainly we see that these should not violate, they should be within the limit. So under level 1, the system is secure, the load is supplied without violating the limits. None of the contingencies, it may be generator outage or line outage, will cause any violation of the system parameters. So none of the contingencies will cause any violation. The system is secure. Network will survive any contingency without the need of control action. So this may be because the severity of this disturbance is very small in that case. In that case, the system we say it is secure. Whereas level 2, so here correctively secure. In this case, all the load is supplied without violating the limits. Again, here also load demand and generation is balanced. Again, it is the load is supplied without violating any limits. Again, remember, we mainly concentrated in voltage and frequency. These two should not violate the limits. In this case, contingencies do not cause any loss if appropriate control action is taken. So here maybe disturbance is slightly severe than the earlier case with respect to level 1. So in order to supply the load without violating the limits, you may have to take some control action. Okay, so maybe you have to see that your automatic generation control, which involves both primary speed control and supplementary control, both should come into action, and then only we can supply the load without violating the limits. So only if appropriate control action is taken, the load is supplied without violating any limits. So level 2, it is with respect to corrective, it is correctively secure. Correct control action has been taken, so that's why the system is secure. Whereas in level 3, it is alert state. Here load is still supplied without violating limits as in level 1 and level 2. But a contingency causes some violations. Contingency means, again, there is a loss of either a generator or any transmission equipment. It causes violations which cannot be corrected without loss of load. So maybe in some part the load has to be shut down. So then only the system can be brought back to level 1 or level 2 by preventing scheduling. So there are so many measures. So one such measure is preventing scheduling. In maybe some area the load has to be shut down. Then only you can supply the load without violating the limits. Okay, so this is alert state with respect to alert state, level 3. Now level 4, here corrective emergency. Here also all the load is supplied but with operating limits violated. Maybe the disturbance is severe here. So our operating limits are violated. All the load is supplied. These violations cannot be corrected without loss of load. So some load has to be shut down, load has to be stopped. So we cannot correct these violations unless the load has to be lost. So the system can be brought back to level 3 by corrective action. In level 5, it is non-correctable emergency condition. So here, all of you hearing? Am I audible? There was some disturbance.
Yes, ma'am.
Okay. So we have level 5, non-correctable emergency, where all the loads are supplied with violation of operating limits. The situation can be corrected only by loss of load. So whereas level 6, it is also representing restorative state, where operating limits are not violated, but the system is operating with loss of load. Restorative control bring back to level 1 or level 2. So these are the various security levels in a power system. Now, functions of system security. System security mainly deals with the operations of power system reliability. System security has three major functions. System monitoring. Monitoring provides the operation of the power system with real-time information on the conditions. SCADA is used to transmit the measurements to a centralized location using telemetry system. Parameters measured are bus voltages, currents, power flows, status of circuit breakers, isolators, outputs of generators, top positions of transformers. Central computer checks the incoming data for violations and immediately violates the operator. SCADA system allows the operator to take control actions to correct overloads out of limit voltages. So then the second major function of system security is contingency analysis evaluation. It is very important. So many faults and disturbance in the power system leads to serious troubles and cascading effects. So causing blackout result in loss of millions of rupees. Hence, contingency analysis tools are main part of the modern energy management system. See, you know that to see that, for example, if there is any loss of generator or transmission line, so there is a violations in the various parameters. So important parameters what we consider is voltage and the frequency. To see that these should not be violated, so we have to do the contingency analysis. It should to happen, we have to do the analysis. So using simulation package, these analysis can be done and we have to do the analysis. Modern operations computers are equipped with contingency analysis programs which models possible system troubles before they arise. These programs are based on model of the power system and are used to study outage events and alarm the operators to any overloads or out of limit voltages. So the third important function is security constrained optimal power flow. See, in the security system also he has to take care that the power flow also should be optimized. See, in this function, a contingency analysis is combined with an optimal power flow, which seeks to make changes to the optimal dispatch of generation as well as other adjustments. So that when a security analysis is run, violations. This function is divided into 4 operating states. See, to understand these 4 operating states, I have given an example here. Okay, with respect to this example, we'll understand. See, first one is optimal dispatch. This is the state of the power system prior to any contingency. It is economically optimal. See, this optimal dispatch means, see, consider this diagram. So here in diagram 1, see, I have shown there are 2 generators. One is of capacity 900 megawatts. Other one is 300 megawatts. Load is connected at bus 2. Okay. So together they have to supply 1200 megawatts. Now the capacity of the power flow in the transmission line is 300 megawatts. We have 3 lines here. So they are sharing out of 900, each are sharing 300. So here total 900 plus 300, 1200 megawatts is supplied to the load. So here this is first diagram is with respect to first statement, that is optimal dispatch. Here this is the state of the power system prior to any contingency. Here you see that there is no outage of any line or outage of the generator prior to contingency. Whereas second one, post contingency, this is the state after a contingency, which leads to non-secure state where there is a violation in line power flows, voltages, etc. See here, this is post contingency. See, there is a outage of the line, and see here in these 2 transmission line, the power flow is more than their capacity, 300 megawatts. That's what here. After the contingency, this leads to non-secure state where there is a violation in the line power flow. There is a violation in the line power flow. Maximum capacity was 300 megawatts, but since this line is not available for service, so 900 megawatts has to be shared by these 2 lines. So there is a violations in the power flow. So this is post contingency. Of course, finally 900 plus 300, 1200 is supplied to the low. Next, third case is secure dispatch. It's a state with no contingency outages, but operating parameters are corrected to account for security violations. So here the operating parameters are corrected. See here, earlier capacity it was 300 megawatts. Now each are sharing 200 megawatts because here it is corrected to 600 megawatts. So this is 600. So total 1200 megawatts is supplied to the load. Whereas in the fourth case, secure post contingency, the state where the system is secure after a contingency occurs. After the contingency occurs, system is still secure. That means here you see the maximum capacity in the transmission line was 300 megawatts. So this is supplying 600 megawatts. So this has to supply 600 megawatts. So corrective measure has been taken. So the total 600 plus 600 is 1200 megawatts. So this is with respect to secure post contingency, the state where the system is secure after a contingency occurs. So after some correct measurements has been taken, so it is secure even after the contingency. So this is about security constraint optimal power flow. Now contingency analysis. So how it will be done? Most common and major failure events on a power system are transmission line outage and generator unit failure. Transmission line outages cause changes in the power flows and voltages on the transmission equipment connected to the system. Generation unit failures also cause power flow and voltages to change in the transmission system. So operator must know which line or generator outages will cause power flow or voltages to fall outside the limits. See, the operators or the engineers should predict if which particular generator or line is out of service will violate these limits. So that has to be analyzed before it has to be predicted. So for this, contingency analysis will be used. So these contingency analysis procedures model for single or multiple failure events are studied one after another. So these fault will be simulated one after another and the analysis will be done until all the possible outages have been covered. For each outage, all voltage and line flows are tested for limit violations. Such a technique is shown in the flow chart. See how contingency analysis will be done. Of course, it will be programmed. We use a simulation package, but you can study the flow chart. You can understand using the flow chart. So initially start, then all the parameters will be input to the system. Then you have to you have to do the load flow. LF represents it is load flow analysis. See, once all the system is entered in the data, you have to do the load flow analysis. So if K is equal to 1, K represents it is a generator, first generator, K is equal to 1, first generation. Simulate outage of generator K and run load flow analysis. We have to simulate the outage of generator. Now in this case, first generator will be out of service. That has to be simulated and you have to do the load flow analysis. Manually it is difficult to do, so it will be done using the simulation package. Load flow analysis will be done. So after you do the load flow analysis, you will come to know the power flow in the various transmission lines and voltages at various buses, active power and reactive power. But here we are mainly interested to see the power flow in the lines and as well as the voltages. So these has to be observed. So after doing the load flow analysis, you have to see any line flows exceeds the limit. If yes, that has to be displayed. Display the message, say particular line I to J, which line I to J is overloaded. If no means any bus voltage is outside the limit. We have to check both the line flow as well as the voltage. So any bus voltage is outside the limit has to be checked. If it is yes, then we have to display that particular bus is either under voltage or over voltage. No, so both has to be checked for the line flow as well as for the voltage violations. Then if SA, it will be displayed. Otherwise, we have to check like this for all the generators. Is it the last generator? Then yes, then we'll go to transmission line outage and we'll do the analysis. Otherwise, we will increment k equal to k plus 1. Earlier k was 1, now k becomes 1 plus 1 equal to. That means second generator will be available out of service. So we are simulating outage of this generator, second generator, and similar thing will be done. This loop will be continued until all the generators are completed. Then if after the last generator, then we'll go to do the contingency analysis for transmission line outage. Now L represents it is transmission line. It is 1. Correct? It is 1. Okay. Then simulate line outage. Again, in the simulation package, all these facilities will be available. You just simulate line outage and run the load flow. LF represents it is load flow. You have to run load flow, maybe using my power. So after this, you will come to know, after doing the load flow analysis, you will come to know any which line may be power flow in that particular line may be exceeding the limit. That has to be checked. If it is yes, display message line I to J is overloaded. If no, you have to check for bus voltage. See, as you have done in the earlier case, generator outage, here also both line flows and bus voltage has to be checked for the line outage. If any bus voltage is outside the limit, then that has to be displayed. It may be over voltage or under voltage, that has to be displayed. Then if not, if it is no, then is it the last line? Because like you have done earlier for generator outage, for all the line, transmission line, it has to be checked. Okay, then if it is not the last line, increment L, that is earlier L was 1, 1 plus 1 becomes 2, then go to B. Go to B, actually B is starting from here. Okay, so this will be continued till all the transmission line outage has been studied. Then finally stop. So this is about the contingency analysis. Okay.